In this example, we are given a fish of an unknown mass that is suspended by strings as shown in this figure. So we have 3 strings, 1, 2, 3. The tension T on the horizontal left string is 5 newtons. So they tell us the tension here is 5 newtons. And they're asking us what is the tension on the string to the right of the fish. They're asking us for the tension here. And they are telling us that this angle theta is 40 degrees. The second question, what is the mass of the fish? In all equilibrium problems like this, the first thing we need to do is identify a particular point in our system and apply Newton's second law of motion to that point. Since we are given a tension T to the left and we are asked for a tension T to the right, it makes sense to choose a point that's common to all these tensions, which would be this point here, where all 3 strings meet. So to the left of that point, we have a force pulling it this way. That's the tension, let's call it TL, that is 5 newtons. And then there is a force pulling it this way. That's TR. That's the tension due to this string. That's what we need to find in part A of the question. And then there is a tension that's pulling it down. That's TB, T bottom. That's due to the gravitational force pulling down on the fish here. Now, because we have equilibrium, TB is just equal to the gravitational pull of the Earth on the fish, just because we have equilibrium. To proceed now, what we need to do after we have identified the forces is to draw a free body diagram. So this is my y-axis, this is my x-axis. Now my TL is along the x-axis in this direction. My TR is in this direction. Since this angle is 40 degrees, that makes this angle is 40 degrees. And my TB is in this direction. Now that I have my free body diagram, I write Newton's second law of motion. Sum of all forces is equal to ma. So in this case, that's going to be TL as a force, as a vector, plus TR as a vector, plus TB as a vector is equal to ma. But since we have equilibrium, we don't have any acceleration, this is just equal to 0. My next step is to write this along the x and along the y if needed. So along x, what do we have along x? What's the x component of TL? That's the full TL, which is, remember, is 5 newtons, but it is in the negative direction. This is my positive x direction. It is pointed the opposite way. So we have minus 5 newtons for TL. What about TR? That's going to be the component of TR along the x-axis. So that's going to be, notice that it is opposite to the 40-degree angle. So it's going to be plus TR, the unknown that we need to find, sine of 40 degrees, since it's opposite to the 40-degree angle. And TB has no x component, so that's 0, equal to 0. You notice here in this equation we have just one unknown TR, so it is sufficient for helping us solve for the So it is sufficient for helping us solve for our unknown TR. So TR is equal to 5 newtons over sine of 40 degrees. Okay, all what I did, I moved the 5 newtons to the other side and then divided by both sides by sine of 40. Which is equal to 7.8 newtons. Now that we found TR, the second question is asking us what is the mass of the fish. To find the mass of the fish, we need to find the gravitational force on the fish, or we need to find TB since they are equal. To find that, I need to write the same equation along the y. Okay, I'm going to write it in the next page. I'll go back here to refer to the diagram. So our equation, remember, is TL plus TR plus TB is equal to 0. Let me just redraw it here. Redraw the diagram here. X, this is our TL, this is our TR at 40 degrees, and this is our TB. So along the y, TL has no component. TR is going to have this component, which is plus the magnitude of TR that we now know as 7.8 newtons times cosine, since it's adjacent to the angle, 40 degrees. And TB is fully in the negative direction, so that's minus TB equal to 0. So our TB is just equal to TR cosine of 40, which is 7.8 newtons times cosine of 40 degrees, which comes out to be 6 newtons. Now to find the mass, M is the gravitational force over the gravitational field. In this case, our gravitational force is just equal to FB. So that's 6 newtons over, using the approximation for G, 10 newtons per kilogram. Newtons cancel out, and we are left with 0.60 kilograms. That's our answer.